the last speaker for today, and we have Jongsoo Park from Facebook AI. And Jongsoo is a technical lead and a manager at Facebook AI Systems Co-Design. And he was earlier at Intel Parallel Computing Labs, and he spent 6 years, and he was a senior research scientist there. So Jongsoo received his PhD from Stanford and then his undergraduate from Seoul National University. Jongsoo has published in several topics, including compilers, data representations, AI frameworks, and recommender systems. And he is also contributing to numerous open source projects. And so today, Jongsoo will be speaking on embedding operations in deep learning recommendation models. So let's invite Jongsoo, and yeah, please start your talk.
Yeah, thanks for the introduction. First of all, can you hear me clearly?
Yes.
Okay, great. Yes. Thanks for inviting me for the presentation. So I'm gonna talk about embedding operations in the recommendation models used in Facebook. And the embedding operations have very interesting implications and characteristics in various systems, aspects of the system. So I thought this can be interesting to present. So I'm gonna first provide a brief introduction overview of what deep learning recommendation model is. And then the later part of the talk, I'll go do more deep dive into the embedding operations specifically. First, DLRM. So this is, we already open source this as a part of the MLPerf benchmark. So maybe some of the audience is already familiar with, but let me briefly go over the introduction. So I guess a lot of people know that the AI is a very central part of Facebook, including like newsfeed and ads recommendation and content understanding for various visual or linguistic signals. And their computation demand and storage demand has been increasing really fast. I think this is also not surprising. But what is interesting is what are the most important workloads and how their breakdown looks like if we look at the overall Facebook's data center fleet. There has been a lot of work, especially in academia, on computer vision and language. But in terms of the server capacity we are using, the ranking and recommendation model is the most important one. And also it has a very unique characteristics compared to other models in computer vision and language. So specifically, if you look at how the model looks like, it exercises various aspects of the system, not just compute. So for example, if you look at computer vision or language models, they are very compute intensive. But in comparison, DLRM is not as compute intensive. So in some sense, it's more balanced. And because of that, it exercises various aspects of the system. Compute, communication, and memory bandwidth and capacity and so on. So regardless whether you are working on compute or communication or storage system, so this can be a very interesting model. And it's not just a recommendation model, but there has been like trend to increase the model size significantly, but the compute is not much as the size. For example, there's interesting work from Google using mixture of experts and so on. So DLRM has also shared some similarity with those kind of more forward-looking models. So if you look at the model architecture, the orange part of the model is actually very similar to the usual computer vision or language models. They are very dense compute heavy. They are doing lots of matrix multiplication. But what's the unique part of this model is related to the embedding lookups. So shown as a blue rectangles. So because of those modules, they stresses the memory, not just the compute, but also the memory capacity and bandwidth, and also the communication part, especially when we are doing the training. So you can look at more details from the the open source website shown at the bottom. And if you also look at the kind of time breakdown of the across various operators, the embedding lookup accounts for a very large fraction of the whole the entire CPU cycles we are spending across our machine learning fleet. So it's comparable to like matrix or convolution operations, those kind of dense operations. So this is the reason why DLRM is important, and especially the embedding part is very interesting. So let me go into more details about the embedding operations. We've been working on various optimization, and each topic can be worth each individual like talk or presentation. So I'm not gonna go into the very details. And the goal of my presentation is gonna be just to make sure it's interesting for the audience. So I provide various pointers so that you can go there and look at the details to know more about this. And I'm gonna talk about some details in the some of the slides, but don't worry too much about not fully understanding those details, because we open sourced a lot of our actual implementations at this open source website called FPGM. So what kind of operations we are doing for the embeddings? So the most straightforward operation, the basic operation is embedding back. It's called embedding back in PyTorch, and sparse length sum in Kappa2. Okay. And we also have a backward counterpart of that. And we also need to do optimizers. It can be a simple SGD, or it can be ADA-grad, or it can be ADAM. Okay. So those are the important operations we are doing for embeddings. And the fourth part of the embedding operation called embedding back in PyTorch looks like this. So let's say we have 3 words associated with FPGM library. It's efficient, low precision inference. And what we do in the embedding back is we look up the associated embedding vectors from the embedding table. So we will have ID associated with each word, like efficient and low precision and inference. In this case, they are 11, 12, 23, and so on. And we look up the associated vectors, and then we do something called pooling operation. And usually that pooling operation is just a simple summation. So in this case, mathematically, this is actually the same as the matrix multiplication, but one of the metrics is sparse because we usually, so each like page, let's say this is FPGM page, is associated with only a few words, keywords, right? So that's the reason why we have a sparsity. And mathematically, we are just doing sparse times dense matrix multiplication. So mathematically, it's very similar, but because the embedding table size is so big, and for high training speed and low latency inference, we want to make this operation really, really fast. And this is why we have many interesting system level challenges. Before going into what kind of optimization we are doing, let me first clarify, when we are optimizing for embedding operations, what are the most important metrics? So there are many interesting techniques, and sometimes they try to trade off between the accuracy and the system level efficiency. But especially for the recommendation model, the accuracy trumps everything. So it's really, really important to maintain the accuracy. And we usually don't take the optimization that sacrifices any accuracy. So the optimizations I'm gonna talk about in the later slides, most of them are maintaining the accuracy while improving the system efficiency. Okay. So there are multiple challenges when we are trying to efficiently execute the embedding operations. So the first one is the sheer memory capacity and the bandwidth demand. So the size of embedding tables is huge. So each of them can be easily tens of gigabytes. and collectively is like hundreds of gigabytes. So they are typically bigger than the like really huge language models. So in terms of the model size, the DRRM is actually even bigger than the language models. And it has irregular accesses, as you saw from one of the previous slides. So you need to do kind of lookup table operations, right? So it's not completely random because the granularity is not individual element. You are looking up the vectors, and vector size is usually like 64 or 120 elements. So you have some amount of spatial locality, but overall it's still kind of irregular access lookup table operations. Still, we want to achieve really, really high bandwidth for the performance. And we routinely see, so if you do the right optimizations, you can actually utilize a high fraction of the HBM bandwidth. So for example, in the latest A100 GPU, using HBM2, you can get more than 1 terabyte per second memory bandwidth. And the demand has been keep increasing. And we want to make sure that when we use like HBM3 or HBM4, whatever future technology, we want to utilize a big fraction of the peak bandwidth for these kind of operations. This is very challenging. So we are also looking at various software level optimizations given the hardware constraints. So these are the optimizations we are already applying today. So the first one, the obvious one, is we are not maintaining the embedding table for everything. So we do some kind of hashing, okay? So of course, there's some trade-off. Let's say two different politicians like Trump and Biden are mapped to the same hash table, same hash ID. Then if we can have some accuracy concerns because they will be mapped to the same embedding vector. But this is some optimization we have to do to kind of contain the growth of the embedding table size. And precision-wise, we've looked at various reduced precision techniques. Like on the training side, we saw that if we use half precision, FP16, combined with stochastic rounding, then we can maintain the accuracy during the training. And inference is usually relatively easy. You can apply more aggressive reduced precision techniques. So we saw that we can even use 4-bit integers during the inference. And on the optimizer side, we are doing optimizations like instead of maintaining the momentum for every element, we can share momentum per embedding vector, so that effectively reduces the memory capacity requirement during training by 2x. We are also looking at memory hierarchy. So usually HBM, in some cases, HBM itself cannot provide enough capacity, or putting all the embedding table on HBM during training can be too expensive. So we are using a memory hierarchy of using HBM as a kind of software managed cache backed by host DRAM. So that's some also important optimizations. So these are the optimizations we are already using it, but we are also interested in more forward-looking ideas. So on the research side, we published a paper that uses a tensor train compression. So it can decrease, it can compress the embedding table size orders of magnitude, but it's still challenging to maintain the accuracy. So I think this is still a work in progress, but very promising direction. And we are also looking at extending the memory hierarchy, not just from between HBM and DRAM, but extending that to SSD. Okay. So doing that, we can further optimize the cost, reduce the cost of the training system. So these are just the ideas, but I'm sure the community in eSPAS have other interesting ideas. So we'll be really, really interested what the researchers in academia can come up with innovative ideas for this operation. Okay, And another challenge is on the backward part or the optimization step of DLRM. So we want to use various sparse optimizers. It can be SGD, or it can be AdaGrad, or it can be Adam. So usually, if you're using linear optimizers like SGD, then it's relatively easy. But if you use nonlinear optimizers like AdaGrad, then there's some challenge associated with sparsity of the optimizer. So specifically, during the forward, as I showed in one of the previous slides, we are just doing a lookup operation, right? That's simple. And usually we access the sparse inputs, sparse matrices in row-wise manner. Okay, so for example, for a given page like FPGM, we access the words associated with FPGM, like efficient library, and then we do the lookup. Okay, so this is forward operation, but in the backward, the math, because how the math works, we have to access column-wise. Okay? So this is not an easy operation to optimize, especially when you have a lot of concurrency. Okay? So one way to work around this is we use something called approximate sparse optimizer. So we ignore the exact numerical algorithm, but we just update embedding table for each individual non-zero. So it kind of breaks the numerics, it's just approximate. Okay. But we are seeing a bigger accuracy gap by using this when we increase the large batch size. So we highly prefer using exact sparse optimizer, but this requires a fast parallel sparse transpose. Because in the forward, we want to access the matrix in row-wise, but in the sparse optimizer, we want to access the matrix in column-wise. So that's the reason why we need to do the sparse transpose, which is not an easy operation to optimize. And the communication is also very interesting and challenging part when you have a huge embedding tables. Because they are so big, we cannot use the simple data parallelism. So this is the most commonly used parallelism methodology for deep learning. So you just replicate all the parameters across all the devices. And then you synchronize using all reduced collective operations. So this is very simple, but we cannot use it for embedding parts of the LRM because they are too big to be replicated. So what we do usually is we use data parallel for dense part of the LRM, but we use model parallel for the sparse part of the model, the embedding part of the model. And because we are using different parallelization methodologies, we have to do some kind of data exchange between them. That usually materialize as an all-to-all operation, or mathematically it's just a transpose, but it's a distributed transpose. And compared to a reduce, which can use hierarchical algorithm, so it usually scales better. All-to-all, we cannot use such kind of hierarchical algorithm. So all-to-all is usually more challenging to scale when we increase number of devices. Okay. So for all-to-all reduce, it's relatively easy to use like thousands of GPUs, but all-to-all is very challenging. So what we are doing is we try to do our best within by software optimizations within the hardware and the network constraint. So one important optimization is we do you apply different partitionings depending on the embedding table sizes and the number of devices we are using for the training. So the simplest way is table-wise. So let's say you have 10 tables and 10 devices, and they are similar sizes, and then each device will just get one table. And then it requires all-to-all communication. So we use kind of table-wise embedding lookup during the embedding part. But when we move to the dense part, we do the all-to-all so that we can transition to the dense data parallelization. Another way is, the partitioning methodology we are using is row-wise. So let's say when one table is so big, so it doesn't fit in a single device, then we have to split that table. And there are two ways. We can partition row-wise or we can partition column-wise. If you do the column row-wise, then it will require reduced scatter. And if you do the column-wise partitioning, then for the input, you need to do all together, basically broadcast. And the after embedding lookup, you need to do all 12. So the details are not very important. You can look at the details from one of the pointers I will provide later. But the main point is depending on the partitioning methodology we are using, so we need different kind of collective communication operations, and it's also a very interesting problem. And we also try to reduce the bandwidth and the latency bandwidth requirement and optimize the latency. So bandwidth is, as usual, relatively easy to optimize. So we can apply various techniques like reduced precision. And we have a paper about this. But I think one of the bigger and a more harder problem is the latency. So for a reduce, it's easy to hide the latency because you can easily overlap or reduce communication with the computation. Okay, but for all-to-all, it's much harder to overlap that with computation, and also the message sizes are much smaller. So I think I think the deep learning community has been mostly more interested in like optimizing bandwidth for a reduced operation, but for DLRM, the latency is also very important. Okay, so in summary, DLRM is a very interesting workload because it stresses various aspects of the system. And those interesting characteristics are mostly from the embedding part of this model. And we have done a lot of optimizations like quantization or various partitioning algorithms, but I believe this is just beginning. And then I think there will be a lot of interesting optimization opportunities out there. And we are trying to open source our work as much as possible. So DLRM is a part of the MLPerf benchmark, and you can consider this as a reference implementation. It focuses on the algorithm and the model. And to complement that, we also open source FVGEM. So you can view this as optimized implementation, but it doesn't cover everything, but it's more focusing on the operators or the corners used for DLRM. Okay, so let me wrap up here and then I'll get the questions.
Okay. Thank you, Jongsoo. Thanks for interesting talk. And yes, please ask questions to Jongsoo. And I already see some questions in chat, so we can start with that. Eric, do you want to ask your questions?
Sure, I had a couple. First, in the second talk, Christian Kestner said that too high an accuracy for recommenders can sometimes be a problem. And he mentioned like for hotel recommendations that people sort of get creeped out when they see that the system is guessing just too uncannily or too accurately what it is they want to do. But you said for Facebook, highest accuracy in the recommender is the paramount sort of consideration. So I just wondered, do you ever see the sort of issue that Christian mentioned? And if you do, how do you deal with that?
Yeah, this is an interesting question, and not sure if I'm the best person to answer. I think it depends more on how we define the accuracy. And I think machine learning researchers are better in better position to answer that question. But I can say that we are trying to balance the kind of specificity and the generalization when we are looking at the accuracy.
Okay. Well, okay. So a more system-y one is the last one that I've got in the chat there. So referring to slide 20 that you had, and you talked about the various partitionings and the trade-offs and so forth. I just wondered how much time does it take, both in terms of a person running the experiments and the machine time, to determine what the best partitioning is for a particular problem?
Yes, for now, we are using a very simple method. We just run a simple dynamic programming algorithm to find a good partitioning. But we do have a reasonable time budget. to try more sophisticated algorithms, because training job usually takes a long time. So it's okay to spend like tens of minutes. Of course, faster will be better. Yeah, yes. Yeah.
Okay. Thank you.
Good. So there are a couple of questions. So first thing is that accuracy itself is tied to some system level optimizations, like what precision arithmetic are you doing, right? So in that sense, do you consider both, or do you consider that you want to maximize the accuracy? Then probably you cannot go with these system optimization techniques, right?
Yeah, at least for now, we are trying to, no matter what kind of system level optimization we are doing, we are trying to maintain the accuracy.
Oh,
so
okay.
our goal is like we don't have accuracy drop more than like 0.02% in entropy, binary cross entropy.
Okay. Okay. Okay.
Yeah.
Okay. And if, for model partitioning that you were mentioning, so model partitioning is known that its performance is highly depending on how you partition the model, right? Because you want to reduce the communication between two partitions because they cross network boundaries, and you want to do as much local compute as possible, right? So then in that sense, as Eric also earlier said, an efficient, if you want to get a good performance out of model partitioning or scaling, then you need a good partitioning of the model. Otherwise, you will not be able to get it. Is that correct? Have you also observed that partitioning the embedding table, how sensitive it is, that how efficiently you partition the embedding table across different machines?
Oh yeah, so the partitioning is very important, and you are asking about which parts it can affect.
Yeah, I'm saying that
the relationship between
how sensitive is the scaling that you are getting to the particular partitioning, to how efficiently you partition it.
Yeah, it's very important. Probably one of the most important optimization for scalability is how we partition.
Right.
Yeah.
Okay.
Yeah.
Okay.
Yeah, and it's not a easy problem, because it's a kind of multi-objective optimization, not just for the communication volume, but also the load imbalance and the communication load balance and the computation balance.
Yes.
Yeah.
Okay, good. There is one more message, I think. No. Okay, no. So okay, any more questions to Jongsoo? Okay, I think thank you, Jongsoo, for an inspiring talk, and thank you very much. This is an applaud from the whole everyone. Okay, yes. Okay. So with good. So thanks. So with that, we come to an end of our workshop, and it was certainly a very interesting workshop with very distinguished speakers and talk and covering different aspects. So I would now hand it over to Eric for the closing remarks, right? Eric, you are on. Yeah.
Okay.
Yeah.
Let me just try and screen show this. It'll let me. Sorry. So yes, thank you all for attending FastPath. For me, at least, it's been a very interesting day. I've learned a lot, and I have bookmarks to learn more. So I hope that's true for everyone who's attending. And I want to thank all of our speakers who really drove all of the interesting content and questions and so forth. So thank you, everyone. We'll be posting as soon as we can, and we're allowed recordings and or slides for each of the speakers. There may be some cases where that is not going to be possible, but where it is possible, we will certainly do that. So please check back on the website. Likewise, please let us know if you have any questions or comments. And I put the email addresses of the three organizers here, Yuhao, Parijat, and me. So please reach out to us if you have any sort of feedback, good, bad, questions, what have you. We certainly welcome hearing from you and really appreciate. I know it's a Sunday and a weekday for many or most or all people attending here, so appreciate your taking this weekend time to attend FastPath. So thank you. And with that, unless someone wants to jump in with a final thought, we'll bring things to a close here.
Yes.
Okay, thank you, everyone. That wraps FastPath 2021.
See you all next year.